This video is all about the exponential form of complex numbers. First, a quick recap from year 12. We saw that we can write complex numbers in Cartesian form, so saying that z equals x plus yi, where x is the real part of the complex number and y is the imaginary part. Or we can write it in modulus argument form, where the modulus is the distance away from the centre, r, and the argument is the angle measured from the real axis. And we saw that we can find both of those things by doing a little bit of Pythagoras to get the r, to get the modulus, and to get the argument we can use inverse tan. We saw that those were the two ways that we could write complex numbers. We were introduced with the first Cartesian method, and then we saw that actually in some cases the modulus argument form was more useful. We're going to see a third way of writing complex numbers in this video. First, I want to show you Euler's relation. This is e to the I theta, e to the power of I theta is equal to cos theta plus I sine theta. I'm not going to prove it in this video, but I am going to link in the description below two other videos that show you two different ways that you can prove this for yourself. One using series, the other using differentiation. It's an incredibly important relation for this video and for the rest of this whole topic. So I strongly suggest you go and watch either one or both of those videos so you can prove this for yourself, because it's extremely important. You don't need to know it for the course, but I strongly suggest you do watch. So we're now going to look at how we can use that result to get a new way of writing complex numbers. So we saw in year 12 that a complex number z can be written as r times cos theta plus I sine theta. That's our modulus argument form. And using Euler's relation, I can replace that cos theta plus I sine theta. So I'm just replacing this with the ei theta. So this gives us our new way of writing complex numbers. This is the exponential form of complex numbers. So my complex number z is equal to the modulus r times e to the I theta, where theta is the argument. So we now have a third way of writing complex numbers. So let's have a look at a few simple cases. So let's consider a simple case when r is 1. If r is 1, then my complex number would be z equals e to the I theta. If theta was 0, if the angle is 0, then I get e to the I times 0, which is e to the 0, which is 1. So if the angle is theta and the if the argument is 0 and the modulus is 1, we get the number 1, as you'd expect. If the argument is pi over 2, then I would get e to the I pi over 2. To work that out, I could write this as cos pi over 2 plus I sine pi over 2. This is me just using the Euler's relationship. Cos pi over 2 is 0. Sine pi over 2 is 1. So I just get I times 1, which is I, which again should make sense. If the argument is pi over 2 and the modulus is 1, then we get the number I. Makes sense. If the angle is pi, I'll get e to the I pi, which would be cos pi plus I sine pi. Cos pi is minus 1. Sine pi is 0. So all of that will just be minus 1, which should make sense. If the argument is pi, and the modulus is 1, I will get to the -1 number. Next, if the argument is 3 pi over 2, I'll get cos 3 pi over 2 plus I sine 3 pi over 2. Cos 3 pi over 2 is 0. Sine 3 pi over 2 is -1. So I'll be just left with minus I, which again should make sense because if I have an argument of 3 pi over 2 and a modulus of 1, then I will get to the number minus I. And then finally, if the argument is 2 pi, then cos of 2 pi is 1, sine 2 pi is 0, so that's all just going to just give me 1, which would make sense. If I have an argument of 2 pi all the way round, I get to 1 again. So those are a few simple cases when the modulus is 1 and the argument has different values. This case in the middle is a very special case. In fact, rather than highlighting all of that, let me just highlight this and this. So e to the I pi is equal to -1. This is what's known as Euler's identity. E to the I pi is equal to -1. This is what's considered to be one of the most beautiful equations in mathematics. In fact, if you type in beautiful maths equation into Google, this is the first equation that comes up. This is the first result that comes up. The reason why this is considered to be a beautiful equation is because you have got the exponential number, 2.7182, blah, 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 which is all about exponential growth. We've seen this in regular maths many times. Any situation where you have exponential growth, where the rate of change is proportional to the amount that you have present at that time, this special number e appears. We've got pi, 3.14159, blah, 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 all about circular measure. This appears as well. And then we've got the imaginary number defined as being the square root of -1. So these three separate numbers, e, pi, and I, which seemingly have got nothing to do with one another. One's about exponential growth, one is about circular measure, one is about the definition of a complex number. These three seemingly completely unrelated numbers are actually related in a very neat, beautiful, concise way. E to the I pi, these very complicated numbers, these irrational numbers, actually come together to form a very simple -1. So you have huge ideas embedded in this one tiny little neat formula. You've got the ideas of exponential growth, you've got the idea of circular measure, you've got complex numbers. These really complicated ideas all coming together in one tidy, neat little formula, which is the special case of our Euler's relation, our exponential form of complex numbers. So that is why this is considered to be one of the most beautiful equations in mathematics. So, just to summarise so far then, we've got 3 different ways of writing complex numbers. The rest of this video is about being able to go between each of these and writing numbers in different forms. So, got 2 questions here. In each case, we're asked to rewrite, instead of being in modulus argument form, we want to write it in the exponential form. So I want to be able to write it in this form. So, first one, I can see that my modulus is root 2, and I can see that my argument is pi over 10. So I can write my complex number z as being root 2 e to the I times pi over 10. And that is my complex number in modulus argument form. For the second example, I can see that my modulus is 5. My argument, now I need to be a little bit careful here because I've got this minus inside there. Now remember from year 12 that in that case what we can do is rewrite this as being cos pi over 8 plus I sine minus pi over 8. Because remember that the cos minus pi over 8 is the same thing as cos pi over 8. And the sine minus pi over 8 is the same thing as minus sine pi over 8. So if you have a minus on the inside here, that means you're just going to flip both of these signs. So our modulus is 5. Our argument in this case is actually minus pi over 8. Therefore, r equals 5e to the I times minus pi over 8. And that's this complex number in modulus argument, in exponential form. Excuse me. Oops. Next, we have got a number in Cartesian form, z equals 2 minus 3i, and we want to write this in exponential form, r e to the I theta. So I want to work out what the modulus is, and I want to work out what the argument of this number is. So I'm just going to draw a little sketch. 2 minus 3i is here. So this is the argument here that I'm going to need to find. This is 2, this is 3. So I can find the modulus by doing some Pythagoras, 2 squared plus 3 squared square rooted, which is going to be root 13. I can find my angle theta there by doing tan inverse, the opposite, divide by the adjacent, which if I do that will give me 0.983. But the angle is below the x-axis, so I know my argument is going to be negative. So I'm going to put a minus in front. I can now write down my complex numbers being r e to the I theta. Next. Okay, so I've now been given a form in exponential, a complex number in exponential form, and I want to write this in Cartesian form. So I can see that my modulus is root 2, and I can see that my argument is 3/4 pi. So if I write this in modulus argument form first, so my r cos theta plus I sine theta. So root 2 times cos 3 pi over 4 plus I sine 3 pi over 4. Cos 3 pi over 4 is minus 1 over root 2. Sine 3 pi over 4 is 1 over root 2. And then multiplying through there, timesing through by the root 2, I will get minus 1 plus I. And that is my complex number. That is root 2 e to the 3 pi over 4 in Cartesian form. Next, we've got two more examples in this video. We want to write our complex number z equals 2e to the 23 pi I over 5 in modulus argument form. So clearly I can see that r is 2 and theta is 23 pi over 5. Now 23 pi over 5, that's an improper fraction, and clearly that's bigger than pi. In fact, it's bigger than 2 pi. So let's find what the equivalent of this is in between minus pi and pi. Just think, 23 pi over 5. That's the same thing as 4 and 3/5 pi, because the 5 goes into 23 4 times. So 4 pi, that's the equivalent of me going pi, 2 pi, 3 pi, 4 pi. So that 4 pi will take me back to where I started from. So I don't need to worry too much about that at all. So the only thing I'm actually going to include is the 3/5 pi. So this will be the same as 3/5 pi. That is in the range that I wanted. So I can now say that my complex number z is equal to 2 cos 3/5 pi plus I sine 3/5 pi. And that is my complex number. Finally, for this video, we are told to use Euler's relation, e to the I theta is equal to cos theta plus I sine theta, and I need to show that cos theta is the same thing as a half e to the I theta plus e to the minus I theta. This is going to be a really useful result later on in this topic. And we're just going to show that it's true in this case. So starting with this, I can say that so I'm just going to write it down to begin with. E to the I theta equals cos theta plus I sine theta. I am now going to write down the same result, but with a minus theta instead of a plus theta. So that will give me e to the minus I theta plus cos minus theta plus I sine minus theta. And as we've seen before, cos of minus theta would be the same thing as cos of theta. And sine of minus theta is the same thing as minus sine theta. Because cos is an even function and sine is an odd function, hence why the minus there just goes there. Right, now look at this line here and this line here. If I add these two things together, so on the right-hand side, I will have e to the I theta plus e to the minus I theta. That's just me adding these two things together. And then on the right-hand side, I would have cos theta plus I sine theta plus cos theta minus I sine theta. Again, we're just adding these two things together. And you can see on the right hand side here, the cos theta plus cos theta is 2 cos theta. And the I sine theta minus I sine theta cancels out. And all I need to do now is divide both sides by 2. So I can say that cos theta is equal to a half of e to the I theta plus e to the minus I theta, which is the result we need to prove, and a result that we're going to use quite a few times later on in this topic. So, just to summarise then, we have now got this third way of writing complex numbers. Z equals Re to the I theta. That comes from Euler's relationship, which again, I do strongly suggest you go and watch the proof for that in the description below. And that also, in a special case where the angle is pi, gives us the most beautiful equation in mathematics, Euler's identity.